Okay, so what happens if we combine what's happening here in chapter 28 and chapter 29? So here I have a current carrying wire, and then some distance r from the current carrying wire, I have a negative charge that's moving with a certain velocity. So I want to know, what is the force on this charged particle caused by the magnetic field? Because the wire produces a magnetic field. The wire's current produces a magnetic field at the place where the negative charge is. So first I have to do is I have to figure that out. I have to say, okay, at this distance here, what's the magnetic field being produced by my current carrying wire? So I'm going to stick my thumb. I'm going to do right-hand rule number 2. Right-hand rule number 2 says that the magnetic field at this location is going to be, if my thumb is this way, it's going to be in, right? I'm going to have all this magnetic field down here at this place is all going to be moving in. Up here, the magnetic field is coming out. Below the wire, the magnetic field is going in. And the amount of that magnetic field, this is an infinitely long wire, so this is 2 pi r. So I can put in my numbers here. So I've got a current. Did I say what the current was? I didn't. So let's choose a current of 10 amps. So I'll say mu naught, 10 amps, 2 pi, and then 0.1 meters. Let's pause. All right, so then I get a magnetic field of 2 times 10 to the negative 5 Teslas. 2 times 10 to the negative 5 Teslas. So then my magnetic force is going to be QV cross this B. Or I can do this, I can say, well, the magnitude of the magnetic force is the magnitude of the charge B sine theta. The angle between my velocity, which is to the right, and my magnetic field, which is in, is 90 degrees. The velocity is like this. The magnetic field is into the board. That's a 90-degree difference between those two. And so my magnitude of my magnetic force is 10 microcoulombs. This is the magnitude of the charge, so don't put in the negative. The velocity is 10 meters per second, the angle, and then I have a magnetic field strength of 2 times 10 to the 5 Teslas, and then the sine of 90. This could be a strength, very, very, very weak force, but nonetheless it's a force, 2 times 10 to the negative 9 newtons. The direction of this force will come from right-hand rule number 1, where I'm going to say V cross B to get my direction. So I put my fingers in the direction of the V. I cross my fingers in the direction of the B. My thumb is pointing up, right? So let's redraw this down here. Here's my charge, Q. Here's my V. And then my magnetic field is going in. So V cross B. My thumb is pointing up, but this is a negative charge. And so the direction of the magnetic force is down. So the F sub B on this particle is 2 times 10 to the negative 9 newtons down negative J, if we wanted to do it that way. So here I've combined both chapter 28 and 29. I'm basically getting, from chapter 29, I'm getting the strength and direction of the magnetic field caused by a current. And then I'm saying that that magnetic field exerts a force that I get from chapter 28 on a charged particle located at that place, pardon me. How about here where I have 2 wires near each other, separated by only 10 centimeters. And they both have current, both of them have current going to the right. Both of these wires produce a magnetic field at the location of the other wire. So wire 1 produces a magnetic field. So if we do our current, we'd sit there and point our fingers in this direction. This has a magnetic field which comes out up here, and it goes in at the location of wire 2. So this is my magnetic field from wire 1. I'm going to actually do my magnetic field from wire 2 in a different color. So for magnetic field of wire 2, if I put my fingers in the direction, my thumb in the direction of this current 2, then up here at wire 1, there's a magnetic field which is coming out. And then down below, it has a magnetic field which is going in. So hopefully that's clear. You have 2 different things here. So wire 1, at wire 1, there's a magnetic field being produced by wire 2 that is coming out of the screen, where the magnetic magnitude of that field is mu naught I2 over 2 pi, and the distance away is that 10 centimeters. And so we can get that magnitude. It's 1 times 10 to the negative 5 Teslas. So then the force on that wire, the force on wire 1 is IL cross B2. And let's say the lengths of these wires, let's say they're both 10 meters. So here we do current 1, which is 10 amps, 10 meters. If I just want to know the magnitude of this force, again, times the magnitude of this magnetic field 2, so multiply that times 100, I end up with 1 times 10 to the negative 3 newtons. But the direction of this force, so let's get rid of some of these purple ones right now, just to try to simplify these things a little bit. We're less concerned about the magnetic field being produced by itself out here as we are at the 1. So if we look at the current for wire 1, the current for wire 1 is moving this way. And then the magnetic field that it's being exposed to is moving out of the board. And so when I do right hand rule number 1, if I say my current, my fingers in the direction of the current, and then curl my fingers in the direction of the magnetic field, I'm going to get that this magnetic force is down. F sub B1 is down. It's attracted to the wire below it. And again, I'm getting that from putting my fingers in the direction, my right hand fingers in the direction of the current of I1, and then curling them in the direction of B2. Goodness, that's not what I wanted here. B2 is out. In this location. I'm also less interested in these. I'm mostly interested in the magnetic fields being produced right at this thing. So the purple here, this is B1 at wire 2. So then if I say force on wire 2, so at wire 2, there's a B1 that's inward to the screen. This is the purple magnetic field that I drew. Where B1, the magnitude should be mu naught I1, again divided by this, but now I1 is twice as large as I2, and so this is going to be twice as large a magnetic field. The force caused by B2, the force caused on the force on wire 2. Let's do it that way. The force on wire 2, which is what I want to know, should be current 2 times the length crossed with the magnetic field being produced by wire 1. The magnitude of that is this current, still the same length, but now we have twice as strong a magnetic field. But this ends up being the same magnitude. We had half the current times twice the magnetic field that we had over here. So Newton would be very thrilled to hear this. He hears that the force that wire 1 exerts on wire 2 is exactly the same in magnitude as the other force. And in fact, the direction here, if we do current 2, we put our right hand fingers in that direction, and now we're going to curl our fingers into the board for the magnetic field. We're going to get a force. Our thumbs are going to point up, which is the opposite direction of the force on wire 2. So Newton would be thrilled to hear that this is up. They're equal magnitude, but opposite direction forces, just like he told us there should be. It turns out if you have two wires next to each other and the currents go in the same direction, those two wires will be attracted to each other. You could go through and prove to yourself that if you have a wire where the current goes this way and then you have another wire where the current goes the opposite way, that the wires will be repelled from one another. And you could actually go through and prove that by switching the currents in that previous problem. The last thing I want to do, Ampere's Law, is a little more involved, so I'm going to cut this video short and do it in a separate video.